This third podcast on acids and bases deals specifically with weak acids and determination of pH. Remember in earlier podcasts I said that the calculation of the weak acid pH involves a little bit more than just negative logging concentration. So let's take the example that you see here on the screen. We're trying to get the pH of a 0.5 molar solution of acetic acid. Now in order to determine pH you really have to have the Ka. So notice that the Ka is stated here on the screen, 1.8 times 10 to the negative fifth. So step one then is to always write the dissociation equation. So what you see here on the screen is the dissociation of the acetic acid into the acetate ion and the H plus ion. So that's always a good place to start. Secondly, just as in previous equilibrium systems, we want to use the ICE table. Now I happen to like putting the ICE table right underneath the equation, especially with acids and bases. Notice that in the question, the initial, when it says it's a 0.5 molar solution of acetic acid, that means the initial concentration of acetic acid is 0.5. And then we are to assume the other two species are not present initially. All of the species are 1 to 1 to 1. The acetic acid is going to dissociate, so that becomes our minus X. The acetate and the H plus are both going to go up by X. And then again, as in previous equilibrium systems, we combine those first two rows, and that gives us the equilibrium concentrations for the three species. So we wrote the dissociation equation. We created the ICE table right underneath it. The next step then is to set up our law of mass action, which is our Ka. And to set up our Ka, we're going to take again products over reactants equal to the Ka. So the Ka given in this particular problem is 1.8 times 10 to the negative fifth. Each of the two species, as you can see on the screen, the two products are both X. And then on the bottom we have our acetic acid, our 0.5 minus X. Now, we haven't really talked a whole lot about the 5% rule, but in acid-base chemistry, because the Kas and Kbs are typically very small, it is possible to ignore the change in X in the denominator and simply write this expression as X squared over 0.5. Now, we can do that because we are assuming the X is so tiny that when you subtract it from the 0.5, it's not going to make any real mathematical difference. Now, you could choose to graph the original 1.8 times 10 to the negative fifth equals X squared over 0.5 minus X. Or if you want to solve this algebraically, you can take out the change in X in the denominator and then simply solve for X. As long as your X value when you estimate ends up being less than 5% of the original value that you would have subtracted it from, then it's a plausible estimate. Okay, so it is possible to estimate here. When you solve for X, that X value is actually giving you the H plus concentration and the acetate ion concentration. Now for us, because we're trying to calculate pH, the most important one of those, of course, then is the H plus. So now we can rely on our pH formula. Our pH formula, remember, is negative log of the H plus concentration. So in this case, our X value was 3 times 10 to the negative third. So we're simply going to negative log that, and when we do, we get a reasonable acidic pH of 2.52.